Okay, welcome back from lunch, everyone. It was delicious. We are certainly very well fed here. So now I'm not standing in the way of you in lunch, but now I'm standing in the way of you in coffee. So I've had some very challenging spots to be in during these lecture series. So today's my third and final lecture, and I'm going to derive for you the expression for the characteristic strain of the gravitational wave background. The point of doing this exercise is so now when you see some timing residuals from a pulsar, you know that you have to cross-correlate these timing residuals. Two terms should pop out. One is the Hellings and Downs curve. The second is the characteristic strain. So we derived the Hellings and Downs curve last time, and this time we're going to look at the second part, that h of f function I told you about, and how that's related to the characteristic strain. Okay, so we're going to go back to the fundamental quantity that we measure, which are the timing residuals. So timing residual from pulsar A at some time tj, and residual from pulsar B at some time tk. And this looks, this should be familiar to you. This is just starting our derivation again from the same point where we left off. This is at tj. This is the ensemble average of all of the red shifts, these fractional frequency shifts in each one of the pulsars. So here we have dt prime, and then here we integrate in tk and t double prime. And then we have the red shifts that are induced in the residuals by the gravitational wave background. T prime, zb, t prime prime. And then I'll start this expression over here. We again have this integral in dt prime up to some time tj, and that's the time at which you take a residual from pulsar A. Remember, those two things are related. And then we have our dt double prime at time tk. And now we write down the Fourier transforms, minus infinity to plus infinity, in df prime and double prime. And we have our z star A, f prime, zb, f double prime with the exponent e to the minus I2 pi f prime t prime minus f prime prime t prime prime. Okay, so this boils down to an expression for the overlap reduction function and the spectral energy content that we're looking at. Tk dt prime prime. And because we have the ff prime delta function, we can just say that this is some f df e to the minus I2 pi f t prime minus t prime prime. And now we have h of f gamma ab of f. Okay, so yesterday I showed you why this function is sometimes a function of f, why the Hellings and Downs curve is sometimes a function of frequency. And that's true when you have very small values of frequency or when the pulsars are very close together, typically within a radiation wavelength of each other. But we were very happy to convince ourselves that for most reasonable interpulsar distances and distances from the Earth to the pulsar, that these oscillations are very rapid, and we can model the pulsar terms, which are the only parts that include the pulsar distance in this expression, with a delta function. That's where the 1 plus delta AB comes from. And that's also why the Hellings and Downs curve is normalized to 1, and why we start at a half, because you get the function doubling from the 1 plus delta AB from the pulsar term. So this is what we did last time. And today we're looking at h of f. Okay. So the cross power spectral energy density, this SAB, and you might remember this from lecture 1 that was in my slides, is gamma AB of F times H of F. So when you cross-correlate your pulsar residuals, there should be two things that pop out, right? The Hellings and Downs curve, which is this gamma AB, and this H of F. So this H of F is going to give you a kind of amplitude that modifies this version of our two-point correlation function. So this is the thing that we actually do with the data. We cross-correlate the data and then outpop these two quantities. So we derived that one, and today we're on H of F. Okay. So in order to understand what is in the spectral content of the gravitational wave background, it's useful to think about the gravitational wave background in terms of its energy density per logarithmic frequency interval, omega GW of F, which we'll define as 1 over rho c, which is the critical density that you need to close the universe. And then this is d rho GW, which is a function of F. And then this is per logarithmic frequency interval. Okay, so the frequency that I have here is the detector frame gravitational wave frequency. This quantity here, I said it out loud, but maybe I should write it down, is the energy density in gravitational waves. Energy density in gravitational waves. And that's in some frequency interval, F plus some F plus DF. And rho c is the critical energy density of the universe, and that is 3 h naught squared over 8 pi. Okay, so your total, your rho GW, gravitational energy density, is therefore this integral of the critical, whoop, here it is, energy density times omega GW df over F. There we go. Okay. So this is all straightforward, but in order to do anything, we have to figure out what this term is, right? So if you open something like Finney 2001, it's a really short derivation of this, and it just jumps into what this quantity is immediately, pi squared over 4 with your factor of characteristic strain. So I wanted to show you where that particular formula comes from. So next thing that I'll derive is exactly what this quantity is and where it comes from, so that next time that you read this paper, it might be a little more clear for you. Okay. So now we derive d rho GW log F is equal to pi over 4 F squared H squared C. I heard a mumbling. Is that just someone talking in their sleep? No? Okay. All right, very good. Okay, so we'll start with the definition of rho GW from linearized gravity. This is pretty much as far back as we can go. 1 over 32 pi. I'm always going to use C equals G equals 1 because I'm not a masochist. And I struggle with minus signs and any factors that I don't need. So rho GW is 1 over 32 pi. And then we have this ensemble average of H naught of H dot ij Tx and H dot j tx. So here the dots are the time derivatives, and this is an ensemble average of waves. So you average over many wavelengths. So if we assume a stochastic and isotropic gravitational wave background, we can express this metric perturbation as the sum of plane waves. So that means that hij of tx is equal to the sum over your polarizations A, integral from minus infinity to plus infinity in df, and then your integral in omega hat, ha, which are your Fourier amplitudes, f and omega hat, e to the 2 pi I f t minus omega hat dot x, and your polarization amplitude A, ij, omega. Okay. So the next thing that we want to define is the spectral energy density. So the power spectral density we denote as SH of F is defined in the following way. So we have H star A of F and omega hat, and then we have some H A prime, F prime, omega hat prime, and this is equal to 1 over 16 pi times delta F minus F prime, delta squared, omega hat prime, and delta A prime, SH of F. I'll probably just put this in the front so that you can see it better. Okay, so this is how we define SH of F. So if we take the time derivative of this plane wave expansion, then we're going to start to get closer to this expression here, right? So we're trying to figure out what the derivative of this quantity is with respect to frequency. We're deriving this expression. We know what this is. We're writing down the ensemble average of these two time derivatives of the metric perturbation. Here is one of them. So we need to take a time derivative of this to figure out what this is so that we can get here and then figure out what on earth this quantity is so we can derive the characteristic strain. Okay, so if we take the time derivative of hij, this is I and j. Are you guys with me so far? Yeah? Okay, you all just had really good lunch, so you're probably feeling a little bit sleepy. All right. This is the sum over A, and then your integral in df, and then your integral in d omega hat, or d omega, it's over the, well, it's the same thing. Okay, times 2 pi I f, ha, f, and omega hat, e to the 2 pi I f t minus omega hat dot x. And then your polarization tensors, EA, IJ, which are a function of omega hat. Okay, so we're going to plug this in to equation 1. Equation 1. I don't think I need to rewrite it. It's right there. And the next thing that we do is that we apply the ensemble average to the sum, right? So if you look at this term here, you see that it eventually ends up in this ensemble average. So now if you imagine, like I do, kind of like taking that and like walking through it, one of the things that you'll have to calculate is the ensemble average of your polarization tensors, right? All right, I'm going to need 10% of you nodding enthusiastically. Okay, that's 13%. I'm rocking this. Okay, good. So into equation one, we want to put this into there. And then we also want to figure out that the sum over A over these EA, IJs, EA, and then IJ is equal to 4. And so the resulting energy density is rho GW is pi over 4, integral from 0 to infinity, in df of f squared sh of f. So we're just applying everything that we learned here. This quantity, when you have two of them from your time derivatives, you're looking at your ensemble average, this thing goes to 4. If you look at your definition of sh of f and apply this, it distills down into this formula here. And we're almost there. That means that the energy density for logarithmic frequency interval is this d rho GW by d log f, and that's equal to f times d rho GW by df. That's equal to pi over 4 times f cubed sh of f. Okay. Very good. So then we define the characteristic strain here. So this is the characteristic strain. As h squared c of f is equal to f times sh of f. And that means that sh of f is equal to the characteristic strain squared divided by frequency. So if you substitute that into this equation here, maybe we'll call this equation 2. Wow, you can really tell when you go from the Hagoromo chalk to the other chalk. Okay, equation 2. And then you get their expression of d rho GW d log f is pi over 4 f squared h squared c of f, which is what we were trying to show. Back to Hagoromo chalk. So nice. Okay, good. These are all pretty fundamental definitions. All right, I can move this one up. Okay. So now that we have that part, we can write down omega GWF is 1 over rho C times D rho GW d log F. And we just saw that that's equal to pi over 4 times F squared H squared C of F over rho C, right, where rho C is defined here. Okay, so we've done a little bit of work, right? We did our light warm up, it's a little jog. And now we need to understand a little bit more about how the energy is distributed in gravitational waves. So now we know how omega GW is related to this critical energy, and we know how it's related to omega GW per logarithmic frequency interval, how that's related to this characteristic strain as we defined it here in terms of SH of F, which is in turn defined up here. But now we want to understand how this is related to gravitational waves. And so we need to write down an expression for the energy distribution of gravitational waves as a function of frequency. Because where we're going in the end is that we're trying to describe the spectral content of the gravitational radiation in the detector, which means we need to understand how that energy is distributed in terms of frequencies, right? So we need to have an expression for dE by d log F. Does that make sense? Feel unconvinced? More nodding, or a question? Clarifying question? No? Maya knows. Okay, so let's look at how we write down dE by d log F, and we'll eventually bring that back into this equation for the final expression for the characteristic strain. All right, so we'll write down dE by d log F. Okay, so we need to know how much energy is emitted in gravitational waves per unit of logarithmic frequency. So the quadruple formula for gravitational waves gives you dE by dt. And that is 32 over 5 times pi f chirp mass to the 10^3 pi f. And the frequency evolution in gravitational waves, f dot, is given by 96 over 5 pi to the 8/3, frequency to the 11/3, and chirp mass to the 5/3. Just as a sidebar, this is a really useful quantity to keep on the tips of your fingers if you decide to work in gravitational waves, what f dot is, and as a function of frequency and chirp mass. And you can normalize this to whatever is best suited for your detector. But sometimes people are curious. They want to know, like, oh, why does frequency evolve so quickly? Like, why do things move so slowly in the nanohertz gravitational wave band versus the LIGO band? And so there's two reasons. One, the frequency is low, you're moving slow, and as the frequency gets high, you see that there's really nonlinear response, and your gravitational waves, as they get to higher frequency, really zoom through your detector. The second thing for pulsar timing is that our masses are huge, and so as you get to higher frequencies, the higher mass ones also evolve really quickly, and the stochasticity of the background breaks down, right? And so there's all of these little astrophysical things that are hidden in these formulas, but it's really good to keep an eye out for them. So really you just have to remember that f dot scales as frequency to the 11/3 and chirp mass to the 5/3. And similarly, your time to coalescence goes like chirp mass to the minus 5/3. You guys can convince yourselves of that later. Okay, anyhow, those are good to keep at the tips of your fingers. But we want d by d log f. And so you can probably guess that I'm going to do a little multiply by 1 trick here, right? So now I have dE by dt, and I have dF by dt, which means I need dt by dF, so that I can write dE by dF is equal to dE by dt, and then dt by dF. So dE by dF, I just plug in these two quantities, 1 over this and this one. And here I have 32 over 5 pi mcf to the 10^3. And then I have 1 over this, so that's 5 over 96 pi to the minus 8/3, chirp mass to the minus 5/3, and frequency to the minus 11/3. So that means that ultimately dE by dF is 1/3 times pi to the 2/3, chirp mass to the 5/3, and frequency to the minus 1/3. Okay, so we're almost there, but we want this written in terms of a logarithm. So we have to hit it with an F. So we want dE by d log f, and that's f times dE by dF. And so I have to multiply this by frequency. So f goes from minus 1/3 to 2/3. So this looks like 1/3 pi to the 2/3, chirp mass to the 5/3, and frequency to the 2/3. Okay, so another interesting note, because we're getting close, right? You can probably smell it. You're like, ooh, frequency to the 2/3. I can probably make that minus 2/3 if I really want to, and we're done. Or maybe that's not what you're thinking. But here we have explicitly assumed that the way that these black holes are moving is through the quadrupole formula, right? Through gravitational wave loss, right? Did you know that? Was that clear? Maybe a little bit, 5% clear, 10% clear. I'm not doing better than 13% with you guys. Okay, so what that means is that this expression, right, for the amount of energy that's input into omega GW and the gravitational wave background really depends on how you assume the black holes are evolving. So here, it's under gravitational radiation. But we know that supermassive black holes need some help merging, right? They can get to within about a parsec and they stall. And that's because they have dynamical friction that initially helps them, this kind of gravitational braking as they're plowing through fields of gas and stars. They're sinking to the bottom of this newly formed galaxy. And then there's other things that happen. There's hardening processes. So a hardening process is anything that brings your binaries close together. And that means things like interaction with gas and stars. And gas and stars are a way for the black holes to get together, right? Very similar, in a similar way to gravitational radiation. It moves the binaries semi-major axis. You can imagine there's a dA by dt, and the binaries are getting closer and closer together. So here we've implicitly assumed that all of the movement here and all of the energy loss is coming from gravitational waves. But that's only true for a certain frequency regime, right? That's only true if your black holes, I hope I'm not spoiling this for you by drawing an f to the minus 2/3 power law. So this is your characteristic strain, and this is your frequency. This is only true from about 10 nanohertz, right? This is your gravitational wave regime. But above that, and we haven't measured this yet with our gravitational wave detectors, but at these lower frequencies, we expect the strain spectrum to turn over. And that's because this way of dE by d log f governing the evolution of the binaries breaks down. There's other physical processes that are much better at helping your binaries to merge than gravitational wave emission. So here you have things like gas torques, stellar hardening, and binary eccentricity that help your black holes to merge. And all of these things are kind of degenerate with each other, right? There's like all of these solutions trace a family of curves that look more or less like they just make the strain spectrum turn over. And so here, you know, the derivation is for gravitational waves, but that's just because we're constraining it to be. This strain spectrum can actually be modeled as a broken power law, if you like, something that looks like this and then like this. And then other funny things can happen here where the stochasticity of the background breaks down. But it's worth noting that this particular solution that we write down that gives us the canonical f to the minus 2/3 power law is really only valid in a regime where gravitational waves are dominating the evolution of the supermassive black hole binary. And that does not necessarily happen at these very low frequencies. Okay? Wow, that's like a 25% head nod. Oh, that's amazing. Okay, good. So dE by d log f, that particular part of the expression is where you can have astrophysics that enters your equation. That's where you can put your own little definition of how the semi-major axis of your binary evolves as a function of time. So you can put in some sort of alpha disk model for gas. You could put in some density of stars around your black hole. You could put in some distribution of eccentricities for your supermassive black hole binaries. Eccentricities are tough. I'm not sure if you guys have seen them in your studies. Has anyone lectured you about eccentric waveforms or binary eccentricity? You all look confused. If it's not circular, if it's kind of like an elliptical orbit. Okay, you seem to know what eccentricity is, but not if you've learned it. Great. Okay. All right, so we have our function for dE by d log f. All right, what's the next thing that we need? Well, we need to write down a connection between our astrophysical population of binaries and omega GW. So let's consider the co-moving number density of binary coalescences per unit redshift and per unit chirp mass. Okay, so let's connect these things. So I'm just going to define this quantity for you, dn squared by dm dz. And this is the co-moving number density. Of binary coalescences. Per redshift and chirp mass interval. So per redshift and chirp mass interval. Okay. So this is a definition. And now we have to be a little bit careful with the frequency that we're talking about in your gravitational waves, because there's the observer frequency and the rest frame frequency. So here, I'm going to say that each binary that I'm describing here emits energy as follows: dE by d log f is pi to the 2/3 over 3 times chirp mass to the 5/3 times frequency to the 2/3. But now this little sub r tells me that that's in the rest frame. And fr is f times 1 plus z. Okay.
In the DE, DL, and F, is that also rest frame frequency?
Here? Yes. Thank you, Emiko. Okay. So now we have to integrate over the whole population, right? This is for a population of binaries. So we've got that part. We've got our energy evolution formula. We're being very careful with our functions of z's. And you can probably tell that redshift is coming into play because now we have a dz here. We have an fr here, which is a function of 1 plus z. So now we tie all of these bits together to write down this gravitational wave energy density, where we want to know at a particular given frequency, if I integrate in redshift, and if I integrate in chirp mass over some co-moving binary population model, some number density of binary coalescences, so some d squared n by dz by dm, that's been properly redshifted in dE d log fr. We combine this expression now here. This is equal to this. And now we have our expression for dE by d log f r over here. And we can put together all of the pieces of the puzzle to solve for h square for the characteristic strain. So we now combine our definition of omega GW with the energy density dE by d log f and d rho GW by d log f. And we get that the characteristic strain squared is 4 over pi f squared times this integral in redshift dz times this integral in chirp mass mc, our co-moving number of binaries, our redshift factor, and dE GW by d log fr. Okay, so we can start to massage this expression a little bit. This is our first attempt at writing down the characteristic strain. We want to make it more useful. So what we do is that we then insert our expression here for dE GW by d log FR. And I need that board space. You guys understand. We just take everything and put it together. Okay, so that means that the characteristic strain squared as a function of frequency is now 4 over pi f squared with these integrals in redshift and in chirp mass. Our co-moving number of black hole binaries. And our cosmology here. And now we have pi to the 2/3 over 3 with our chirp mass to the 5/3. And then our frequency times 1 plus z, all to the power of 2/3. Okay, so we're almost there. Now we have 4 pi. I'll just bring this pi to the 2/3 out to the front. And then I have 3 pi, right? 3 out here on the bottom. And now I have all of my factors of f that combine together. So I have 1 over f squared here. And here I have f to the 2/3. And so this gives me f to the 4/3 on the bottom. Then I have my integration in redshift and in mass. And now what's left is my number of supermassive black hole binaries per co-moving volume, dz by dm, and I have my chirp mass to the 5/3, and I have my 1 plus z expression to the minus 1/3 because I had 1 here, and now I have 2/3 here. So this is minus 1/3 here. Okay. So this leads us to our final expression, which is 4 over 3 pi to the 1/3 f to the minus 4/3 and d squared n dz by dm, chirp mass to the 5/3, 1 plus z to the minus 1/3. Okay, so a few comments about this. Number 1, we found that the characteristic strain of a stochastic gravitational wave background squared scales like frequency to the minus 4/3, meaning that the characteristic strain itself scales like f to the minus 2/3, which is what you saw in my talk, what I wrote up here. And that's the final answer for gravitational wave-driven supermassive black hole binaries. It's important that you remember that the shape of the strain spectrum actually contains a lot of astrophysics in it. Even the point where it turns over can tell you about the density of stars that surround the cosmic population of supermassive black hole binaries. The other thing is that the strain, this characteristic strain, is a really strong function of the supermassive black hole masses. In fact, it's the strongest thing contributing to the gravitational wave background. So that's why Matthias and Gabby, I don't know if they're in here, are so interested right now in figuring out what the black hole masses really are, or saying, maybe the way that things are measured are slightly inconsistent. Do you remember Jenny Green's talk? She gave you this really nice overview of how black hole masses are measured and how if you measure them using different techniques, you can't even get consistent masses. right? And that's a big problem for making models of the gravitational wave background when your number one thing that affects the amplitude of the background is your black hole mass, right? So it's very sensitive to your black hole mass. The characteristic strain squared goes like the Chirp mass to the 5/3. So I'm going to leave that picture up there. And just try to take you to where we're at right now with these measurements. So we know that the characteristic strain scales like some amplitude times frequency to the minus 2/3 that we typically report at a reference frequency of 1 over a year. Okay, so you'll see that I've been sort of dismissive of all of the work that we've done. And I've said all of this, including this little guy up here, all of this stuff just gives you some amplitude that you can measure. That is A. So when you make a measurement with pulsar timing arrays of the gravitational wave background, what you're actually measuring is this cosmic merger history of supermassive black hole binaries that's integrated in mass and integrated in redshift. Now, for those of you who are studying astrophysics, this is a special sidebar for you. This is where things like your black hole mass function become important. You're not actually integrating from 0 to infinity, are you? You're probably going from 10 to the 7 or 10 to the 8 to whatever the end of your black hole mass function is, right? You're also not integrating to infinite redshift. You'll find that your population will peak at maybe redshift 2 or 2.5, and then you're done, right? You don't actually get a signal out to redshift infinity. So these are all astrophysical quantities that you can constrain. Furthermore, this guy here, this number of binaries, how would you relate this to quantities that you can measure, that you can see in space? How do I figure out, did I write it down? This co-moving volume, this number of supermassive black hole binaries per unit redshift, per unit chirp mass. How is that related to an astrophysical quantity? It's not a trick question. You might think that answer's too easy. That's the answer. Can we actually measure black holes directly that are at really far distances? No. But where do the supermassive black holes live? Yes, that was like 50%. Great. Yes, they live in galaxies. And so if the black holes are merging, that should roughly trace what? Galaxy mergers. Exactly. So this closely traces galaxy major mergers, right? So when two galaxies that are roughly the same size, technically speaking, a major merger is 4-to-1, then you get something that comes in here. So this is really the number density of galaxy mergers, right? You can trace this with galaxy mergers, and then you have some delay time between when the galaxies merge and when the supermassive black holes merge. And that's a quantity that we can constrain with our measurements. Okay, so where we're at right now, the gravitational wave background, is that we've finally made a measurement of A, this amplitude A, right? And we found that A is 2.4 times 10 to the minus 15 at a reference frequency of 1 over a year. Why do I have to give a reference frequency when I give an amplitude of the background? Yes, that's right. It's sloped, which means that it has an amplitude as a function of frequency, right? So if I give you an amplitude, that's not really super informative, right? You have to tell me what frequency that amplitude is at. And if you want to compare results from different detectors and you want to do some sort of apples to apples comparison, you have to, of course, say at what frequency you measured this amplitude of the background. So we measured this amplitude is 2.4 times 10 to the minus 15 at a reference frequency of 1 per year. And this was the big nanograv result that was in the New York Times, all over the place. In 2023, we had a big press conference at the National Science Foundation, but we found evidence for this gravitational wave background with this amplitude of 2.4 times 10 to the minus 15. What are the units of this amplitude? Or what are the units of the characteristic strain? What are the units of strain? Right, if strain is dimensionless, what happens when I add a whole bunch of things in quadrature that are dimensionless? What's the dimension? It's still dimensionless, exactly. So this is a dimensionless quantity, right? This is the amplitude. So now we have this amplitude that we measured. How do I relate it back to these cross-correlated timing residuals? Okay, you guys need more coffee. I'm going to help you because I'm pumped. Okay. So let's see. I think we can start from here. All right. Page 2. There we go. Okay. So we have our expression for the cross power spectral density in gravitational waves. It's a function of gamma AB, which is the Hellings and Downs curve, and this h of f. So h of f we can now write down as 1 over 12 pi squared, 1 over f squared times sh of f. And using the definition of the characteristic strain, we know that sh of f is equal to h squared c over f. That means that h of f is ultimately 1 over 12 pi squared h squared c of f over f cubed, and that this measurement that we make when we cross-correlate all of the timing residuals, this SAB of f, is equal to gamma AB, this Hellings and Downs curve, times h of f, times 1 over 12 pi squared h squared c over f cubed. So what does this mean in practice? It means that when we actually looked at this cross-power spectral density, what we saw was a combination of the Hellings and Downs curve that had some sort of amplitude to it, right? Because here you have something that's purely geometric, right? This starts at 1 for the autocorrelation, then drops to a half and makes a little swoopy shape, and then comes up to 1/2 of the value that it was before, right? So you have the Hellings and Downs curve that looks like this, right? It's not a pure quadrupole. It's got other things in it. If it were a pure quadrupole, then the minimum would be at pi over 2, and it's not, but that's not the point here. So this is pi over 2. Let's just say that this is pi, this is 0, this is a half, this is 1. Okay, so when we have our pulsar pairs, our AB pulsar pairs, it means that I have one pair of pulsars here that's correlated by some angle, right? This here is the angle. I drew an xc, but you guys know in your notes that it's really a zeta, right? Yeah, okay. You guys will now suffer from the zeta xc degeneracy. So this is your angle between your pulsars, and this is your Hellings and Downs curve, or your overlap reduction function. So if your pulsars are separated by some small angle, this gives you a point here on the curve. If they're separated by another one, right, you eventually populate this curve with all of your pulsar pairs. Now, in reality, what you do is that you measure this guy, right? You measure this, and you know that it should have some sort of shape that's a function of the angle between your pulsar pairs, and some sort of amplitude that's given by the characteristic strain. So if the amplitude that we measured at a reference frequency of 1 over a year is 2.4 times 10 to the minus 18, it means that what we have over here is going to have some a squared that multiplies it, right? Because you have a characteristic strain squared, which gives you an a squared. And so this is going to be of the order of 10 to the minus 29 to 10 to the minus 30, right? That's just the order of magnitude you get for the measurement that you made. Does this all make sense? Good. So when you do your big reveal, what you find with your data is that you've measured something, right, that looks like this. It's not perfect. It's not even close. Some things are better measured than others. But you've measured your cross-correlated pulsars, and sometimes they follow the Hellings and Downs curve, and sometimes they don't, and sometimes they're super, super messy. Sometimes they're floating up here. But if you make something like a 3 sigma detection of the background, which is what we did, between 3 and 4 sigma, depending on the particular statistic that you choose, this is actually what comes out when you cross-correlate all of your pulsar residuals. Does this make sense? Okay, so I think the last thing that I'll mention is this up to the minus 2/3 versus gamma 13/3. It's just good to know. So your characteristic strain scales like frequency to the minus 2/3. This is the really famous Finney 2001 result. So it means that your characteristic strain squared goes like frequency to the minus 4/3. And if you're plotting your cross power spectral density, then you have this extra f cubed on the bottom. And so if you're plotting this SAB, then this you have to subtract 3 from. And this gives you 13/3. And we call this guy gamma, and this we typically call alpha. And so when you're looking for a population that's sourced by supermassive black hole binaries, or even from just regular stellar mass black holes, it doesn't matter, you're looking for some sort of amplitude of red noise in your detector that scales like frequency to the minus 2/3. But this is where I'll kind of take you a little bit off the beaten track, right? What if the source of your background is not astrophysical? What in this derivation remains the same? I know, right? It's a mind bender. I'll just tell you the answer. If you have a primordial gravitational wave background, so say that your gravitational waves come from quantum fluctuations in the early universe, and you're really interested in like Grishchuk's 1975 papers and that kind of stuff, which is really fun to read about, then you'll probably have some sort of figure in mind where you look at omega GW and frequency, and you're going to have pulsar timing arrays here, and you're going to have LISA here, and you're going to have LIGO here, and you're going to have CMB measurements over here. And you know that your energy density in gravitational waves from a primordial background should be asymptotically flat if there's any justice in the universe, which there may not be. But this should have a tensor index of about 0. The only way that you can make a measurement of something primordial is if this is not true. And this would violate standard cosmology, right? If your tensor index is not asymptotically flat. If it's blue, do I have blue? I have blue. Then you start to get into really kind of fun and exotic physics where you have some NT that's greater than 0. So these are theories like ekpyrosis, or you have bouncing universes or bouncing cosmologies. Finally, a question. The tensor index, oh geez. I don't have the formula written down with me, but I'll send it to you. It's just another way of writing down omega GW. There's the scalar index and the tensor index, and they're related to omega GW. And in this instance, we're just looking at the tensor one because it's supposed to be flat. And the reason that I was mentioning this is because if that's flat, then that means that this thing is invariant, right? That this frequency should go like f to the -1. Okay, if you have a background from cosmic strings, it's -7/8. And so one of the things that we're doing now with pulsar timing is that we're trying to actually measure the tensor, actually trying to measure this. We're trying to measure the power law index because that tells you what's sourcing the gravitational wave background. So is it -2/3? Is it -1? Is it -7/8? Right now, it's all of those things. It's not really close to 4.33. I actually forget what the median value is. Where's Bjorn? Bjorn, do you remember what's gamma right now? 3.3? 3.2? Right? So supermassive black holes is 13/3, right? Which is 4.3. But what we actually measure is 3.2 with some pretty big error bars, which means that we don't actually know what's sourcing the gravitational wave background. We think it's supermassive black hole binaries. We think that there's maybe some pulsar noise or something that's causing something weird happening in the strain spectrum. Maybe there's a continuous wave source that's stacked on top of the background that prevents things from being perfectly 4.33, because again, this is from the ensemble average, right, over multiple universes. So we don't really know. So I want to close out by saying that you've now learned how to take timing residuals from pulsars. Don't take them on your own. Ask a friendly neighborhood radio astronomer. My former postdoc is the last person who used Arecibo, and you saw what happened there. So don't, as a theorist, ever take data. So when you cross-correlate your pulsars, out pop two things. You're going to have this angular correlation function. Just drop some of this chalk. Angular correlation function, which is the Hellings and Downs curve. I told you last time when we were deriving the Hellings and Downs curve that this can also contain new physics, right? If you have a breathing mode, for example, that would look like this. It's a completely different looking correlation function. So that's kind of cool. Your correlation function has some sort of amplitude that multiplies it. This amplitude tells you about what's sourcing your gravitational wave background. This doesn't. Anything that creates gravitational waves will give you this geometric term. This doesn't tell you if it's supermassive black holes or cosmic strings or domain walls or any other kind of topological defect in the early universe. That's not here, it's here. And so this amplitude, again, will tell you about the astrophysics of what's happening in your strain spectrum. If it's supermassive black holes, your characteristic strain amplitude can tell you about your black hole masses, because your characteristic strain squared scales as your Chert mass to the 5/3. And so when you change your black hole mass, you can move the amplitude of your background up and down, but it's still a power law, right? You just shift it up and down as you change your mass. As you change the physics that's driving your binaries, then you can make your strain spectrum turn over like this, right? That's gas and stars and eccentricity. That doesn't affect the amplitude in general. Of course, there's those exceptions. But it changes the shape of the strain spectrum. So when you're doing a pulsar timing ray experiment and you're cross-correlating your residuals, You're gaining insights into if your gravitational waves are Einsteinian or if there's extensions to general relativity that are hidden in there through this correlation function. If your background is isotropic or anisotropic, that all comes in here. And you're starting to understand how your gravitational radiation scales as a function of frequency. And that can tell you about what's sourcing the gravitational wave background. Is it supermassive black holes, primordial gravitational waves, domain walls, other things, cosmic strings? And again, this amplitude itself will tell you about the black hole masses. To first order, it's the most important contribution that you have to the characteristic strain, to this gravitational wave background, because the characteristic strain squared scales as Chirp mass to the 5/3. And the shape of the strain spectrum tells you about the physics that's driving your black hole mergers if you think that your gravitational wave background is astrophysical. So pulsar timing arrays are really this very rich physics experiment where you have all of these different possibilities to constrain and to learn about the early universe. So thank you everyone for your attention. Whoa, yeah, questions? Yeah.
So if you potentially have this LIGO type problem where you can have a dominating contribution from one source, but then, I mean, that doesn't work the same with pulse timing, but if you subtract away that.
Yeah. Oh, there's nothing at all preventing you from having some sort of A total squared. That's A squared supermassive black hole binaries plus some A squared cosmological or primordial plus whatever terms you want. I think that they're going to be difficult to disentangle in the near future. But I think if we're clever monkeys, we'll figure it out. So you're totally right. There could be other contributions. I worry that the other ones are very, very small. And so maybe your students will find it, but you can write the first paper. Okay, you have another question? Oh, wonderful. Great. Yeah.
So, the FDT, said something about the contribution from the chirp mass.
Yeah.
And stochasticity.
Yeah, so when you're at these higher frequencies, there's fewer, on average, supermassive black hole binaries per unit frequency. And that's because your frequency evolution, right, your f dot goes like f to the 11/3. So now these things are going faster than usual. To give you a sense of scale, an equal mass binary at 1 nanohertz, if it's a 10 to the 9 solar mass binary, is like tens of millions of years away from coalescence. If it's at 100 nanohertz, then it's about 100 years away from coalescence. So the evolution gets a lot faster as a function of time, and it's also a function of mass, right? Your time to coalescence scales like Chirp mass to the -5/3. So the more massive your binaries are, the faster they run away. So that leads to an overall paucity of supermassive black hole binaries at very high frequencies. And so you can't really say that you have a stochastic background because it's not even clear that you're in this confusion limit. You might just be able to individually resolve all the black holes that are there. Okay, yeah.
I guess I have the same question with the first one, but for the gamma term. So if we have like the OGR polarizations,
Yeah.
the upside tends to be.
Yeah.
It would be like a contribution from that. Like would it be like slightly up there and down first?
Well, I think that the way that you would do it is that you would have different weights, right? You would have like your plus, cross, and your breathing mode polarizations, and you would have this gamma for each one of them. So then this becomes like a series of gammas, and each one of them would have some sort of individual weight in front of it, and you would do a Monte Carlo to measure those terms to understand the contributions of them together. Yeah.
Is there maybe follow up?
Yeah.
Is there a way to select some pulsar in the sky that would like highlight any of these contributions better than the other? Like, is there a better selection for, let's say, looking at the scale of like really?
Yeah. So Yeah, so there's one of the modes, I can't remember which one it is, but one of them has like the direction of gravitational wave propagation, stretching and squashing as it's going, right? And exactly like this. You can really easily rule that out because that would have been measured 15 years ago. So that's one thing that you can say. Yeah, that's right. Yeah. Yeah.
Expression for the E by dt log n.
Yeah.
Term, which I think you will face. So the explained as Chapman's to the power of that and redshifted frequency.
Yeah.
Shouldn't the Chapman's also be redshifted?
You can redshift either the frequency or the chirp mass. You can choose one or the other. It gives you the same result. Yeah. Aha.
So this would be Chiara mentioned wrestling sort of the leading one for the whole.
Yeah.
Now, is it ever important to do higher directions, particularly in the context of like testing gel currently?
Well, you tell me, right? If the first order strain is 10 to the minus 15, it means that second order H squared is 10 to the minus 30. So I mean, off the top of my head, I haven't actually looked into it, but I think that's how it works. So I don't think that that would be important anytime soon. But there could be another way of probing those effects. Like if you were looking at spin terms, for example, and how the waveform is evolving between the Earth and the pulsar, then you could look at the post-Newtonian expansion. And you can look at, up to spin-spin coupling, and that would like add and subtract different phase terms in the waveform, and then that would like make your pulsar distance closer or further away. So if you could fix that, then you could potentially measure your waveform in that sense. So you could kind of skirt around it that way. But I'm not sure like directly second order corrections if those are measurable in any kind of reasonable way. I'm just not sure. Okay, I think I'm running out of time. Will the host permit me one more question? Okay, yeah.
Okay, so should we consider the combination of each system where you're viewing by ear? Because
Sorry, should we consider what?
inclination angle.
Yeah. So for the stochastic background, you take a sky and polarization average quantity to compute the strain typically. You average over all those terms. Yeah, I mean, there's a lot of stuff that's swept under the rug to keep it to 75 minutes. But you could definitely go deeper and write down complete waveforms and average over all of those terms. In fact, when we're doing continuous wave searches, looking for the individual potentially sinusoidal, like monochromatic waveforms, even then we do sometimes all sky searches where we still average over the phase, the polarization angle, the cosine of the inclination angle. We just get some sort of amplitude. Yeah. Okay. All right, one more question, then I gotta go. I got a train to catch. Yeah, so the galaxy merger rates are in the d squared n by d, dz by dm term, which is gone now. The black hole mass is the most important thing, right? So if you think about the characteristic strain squared, you have the chirp mass to the 5/3, and then the merger rate is basically linear, right? And the other one is to the 5/3. So that's going to impact everything the most. And that's why we need to get better black hole mass measurements, better estimates on these empirical scaling relations, maybe even breaking the power law, as Gabby and Matthias did, saying that maybe this is not one power law, but two power laws, and we can find evidence for a break. But better understanding how black hole masses are related to galaxy masses and how to measure any of these things is really important. Okay, you guys can email me if you have any more questions. I'm so happy you were actually following along. I thought it was at like a 10% level, but you guys were actually really, really good. So thanks again. And this has been really fun. Thank you.